Hello everyone, welcome to my channel. In this video, we'll discuss about FETs, which is Field Effect Transistor. In the FET, if you see here, we have three terminals. One is source, other one is drain, the other one is gate. We already seen in the case of a BJT, there are three terminals, emitter, base, and collector. Emitter will send the charge carriers. Collector will collect the charge carriers. Where base is used to control the charge carriers which are moving from emitter to collector. So the roles of this FET is also the same thing. This source is used to send the charge carriers and drain is used to collect the charge carriers and gate will control the charge carriers which are moving from source to drain. That's it. Now, if you see here, in the case of a BJT, we have been seeing the two types of BJT. One is NPN, the other one is PNP, right? Whereas in the case of FET, here there are two types we can see. One is N channel, the other one is P channel. And of course, this FET is again classified into two types, that is JFET and MOSFET. But in that again, there are only two types, that is N channel and P channel. Whereas in the BJT, the conductivity or current flow is happening due to both the charge carriers, majority and minority charge carriers. Whereas channel, the conductivity will take in place only because of electrons. Whereas in the case of a P channel, the conductivity will be taken place only because of holes. So that is why the other name for this FET is a unipolar device. Is a unipolar device. But because its conductivity is mainly depends only on the majority charge carriers. And the other difference between these two is that in the case of a BJT, in the BJT, we have been seeing that its output characteristics like output current, output voltage, everything can be controlled with the help of input current. Whereas in the case of a FET, that everything can be controlled with the help of an voltage. With the help of a voltage. So in this way, just these are the points. So these are the points like FET is a three-terminal device that is source, drain, and gate, and that can be all the output characteristics like output voltage and output current can be controlled with the help of an input voltage. And the other name for this FET is a unipolar device because it depends only on the holes or electrons. Now, if you see this FET is again classified into two types. One is JFET, Junction Field Effect Transistor. The other one is MOSFET, Metal Oxide Semiconductor FET. We'll see this, why it is called as JFET, why it is called as a MOSFET. We'll see that. Now, in the case of a JFET, FET is classified into two types. One is N-channel JFET, the other one is P-channel JFET. In the case of a MOSFET, we can say there are two types of MOSFETs out there. One is depletion MOSFET, the other one is enhancement MOSFET. In this depletion MOSFET, it is classified into two types again, that is N channel and P channel. Similarly, in the enhancement mode also, that is N channel and P channel. So basically, if you see, there are six devices are there. In the case of FETs, one is N channel JFET, the other one is P channel JFET. The other one is N channel depletion MOSFET. Next one is a P channel depletion MOSFET. The other one is N channel enhancement MOSFET, like that. The other one is P channel enhancement MOSFET. So like this, there are six FETs are there. In this case, we'll discuss, here we will discuss only N-channel JFET and N-channel depletion MOSFET and then N-channel enhancement MOSFET. There is only small difference between, there is only small differences there between depletion and enhancement mode MOSFET. We'll see that. So if you understand this N-channel JFET, then you can clearly understand about this P-channel JFET. Here we'll discuss clearly about N-channel depletion mode and N-channel enhancement mode MOSFET. You can understand the other one. So now directly I'm going to the N-channel JFET. First, we'll see the symbol. This was the basic symbol of this N-channel JFET. And if you see its internal construction, first of all, we'll take a pure semiconductor. In that pure semiconductor, we'll add pentavalent impurities. We'll add pentavalent impurities. Then it will turn into an N-type semiconductor. By adding pentavalent impurities, it will turn into an N-type semiconductor. So on the two sides of this n-type semiconductor is connected with an ohmic contacts. And there one terminal we will call it as a source, the other terminal we will call it as a drain in this way. So we already know this source will send the charge carriers. Here it will send the electrons. The drain will collect the electrons. So in between these two gates should be there. That should be control the electrons which are moving from source to drain. To indicate gate terminal, trivalent impurities are added on the two sides of this n-type semiconductor. Then it will turn into a p-type on the two sides. Again, ohmic contacts are taken on the two sides, and these two are internally shorted. These two are internally shorted. Before sorting, we can see these two different terminals, but these two are internally shorted, so that is why we can see only one terminal. Why? Because these two are internally shorted. Then this terminal we are calling it as a gate. That's it. Now source will send the charge carriers, and the drain will collect the charge carriers. Whereas this gate will control the charge carriers which are going from source to drain. And path of these electrons which are going from source to drain, this one is called a channel. This is called a channel. So, so this is the construction of this n-channel JFET. Basic points. Just take a snapshot of this one. Take a snapshot of this one, and then take a snapshot of these points. What are the things we have been discussed? All the things have been put it in the form of points. Now the next one. How this JFET will looks like. If you see here, in the case of whenever there are two regions are there, that is n-type and p-type. In between these two, we can see some depletion region. We can see some depletion region. We already know this, right? Whenever there is an a p-type and n-type are there, and between these two, there is formation of depletion region. So similarly here we can see this n-type and p-type. So that is why there is a formation of a depletion region in between these two. So here in this case, we can see this channel. Channel is already available. So by giving this connection across source and drain, these charge carriers can move from source to drain. But because channel is already available, right? So thing is that let us try to give a connection here itself. Now I want to send the electrons from the source. I want to send electrons from the source. I want to send an electrons from the source. If I want to send an electrons from the source means which terminal should I have to connect it? Should I have to connect positive or negative? That is the question. So here electron should be repelled. Electron is a negatively charged particle, right? And that will be repelled for a negative terminal. So that is why here I have to give negative terminal. But because this electron has to move from here, it should be repelled from here. And here electrons should be collected at the drain side. So that is why here I have to give a positive terminal. Here I have to give a positive terminal like this. So this is the basic connection, and this is a voltage we are calling it as a VDS. Now, by connecting in this way, these electrons will move from source and drain will collect the electrons. Next, we'll see about the gate. Now, with the help of this gate terminal, by applying some amount of voltage, these electrons we have to control it. For this case, we are applying a reverse voltage at this gate terminal. The reverse voltage means this P should be connected to the negative. And here we have to give positive to the source. And this voltage we are calling it as a VGS. What happens whenever we are applying this reverse voltage? Then what happens to this depletion region? If we are going on increasing this reverse voltage, if you are going on varying this reverse voltage, if you are going on increasing this reverse voltage in negative direction, then whatever the depletion region is there, that depletion region also goes on increases, right? When the diode is connected in reverse bias, then what happens to the depletion region? It will be increased, right? Here also. Here there are two regions are there, that is P and N regions, and these we are connecting in the reverse bias. So that is why By increasing this reverse voltage, this depletion region also increases. This depletion region also increases. So by increasing this depletion region, what happens to the channel? The channel width will decrease. Very simple. If I increase this VGS, then depletion region will increase. By increasing this depletion region, what happens to the channel? The channel will decrease. It means whatever the current is there, the current is decreasing. But because the charge carriers which are going from source to drain is going on decreasing, right? So that is why the drain current will be decreases. It means internal resistance is increasing. So that is the connection we can give it here. So here we had a VGS in negative and VDS is positive. In this way, we are controlling. Actually, by giving this VGS in negative, we are controlling the charge carriers. We are decreasing the charge carriers. Somehow, increment or decrement, we are trying to control the charge carriers, right? So we are controlling these charge carriers by giving a reverse bias with the gate terminal. So if you see this one after the other, in the case of a VGS is equals to zero here, I'm saying. Here I'm not giving any kind of VGS voltage. This VGS is zero here. Here VGS is zero. I'm not giving anything. This I is directly shorted to the source. So by applying this VDS voltage, these electrons can move from source to drain, and maximum channel is available. Initially, maximum channel is available. If I start giving this VGS in a negative direction, then this effective channel will be decreases. Why? Well, because this depletion region will be increases. Due to that, the effective channel will be decreases. In that way, the number of electrons which are moving from source to drain is also decreases. So the current also decreases. At some particular point of this voltage, the channel is completely closed. The channel is completely closed. This is called as a cutoff region, and this region is called as cutoff region. The depletion region will be maximum, and the channel is very, very minimum. That is completely closed. That is called as a cutoff region. In this way, if I slowly increase in this VGS, this is the thing we can see in the MOSFET. Graph of the transfer characteristics. This was the VGS. This was the drain current of ID. Initially, at zero voltage of this VGS, the current is maximum. Let us say this current, I'm indicating this current right here. If I start increasing this VGS in negative direction, then effective channel is decreasing. It means current is decreasing. So current will slowly decrease like this. At some particular point of voltage, the depletion region is maximum, the channel is zero here. So that no charge carriers are moving from source to drain, so the current is zero. At some particular point of voltage, the current is zero like this. This is the graph we can see in between from VGS and ID, and that we are calling it as a transfer characteristics. This is the transfer characteristics of N channel JFET. These are the points we have been discussed. Just take a snapshot of this one. We'll move on to the next one. Now, we'll see the effect of VDS when VGS equals to zero. Previously, we have been taking a constant of this VDS. We changed only this VGS, right? We have been varied this VGS and we kept VDS as constant. Now, what we see here in this one, we'll consider VGS as a constant and we'll try to vary this VDS. By varying this VDS, what happens? Let us say this VGS equals to zero. If I say this VGS equals to zero, there is already some channel will be there, right? Now I'm slowly increasing this VDS. So if I slowly increase this VDS, let us take a graph of these two in between from VDS and ID. If I see, then in this case, if I slowly increase this VDS means the intensity or the velocity of the charge carriers, if I slowly increase in this VDS, the velocity of the charge carriers is also goes on increases. In that case, current also increases. So by increasing this VDS, current also goes on increases. At some particular point, it increases. Let us say that VDS equals to 2 volts applying here. If I given a VDS equals to 2 volts means here the maximum voltage will be there. That is 2 volts. It will be slowly dropped in this channel at some point 1 volts. At some point it will become around 0.5 volts like that. So if you see here, this is a 2 volts which we are giving a positive voltage at the N and P regions, which means here we are giving again a reverse voltage only. Observe this point. This is a 2 volts. We are giving indirectly a reverse voltage only for N and P regions. If I give in this way, then what happens? The maximum voltage will be there at the drain side and the minimum voltage will be there at the source side, right? It means maximum reverse voltage is there at the drain side. Minimum reverse voltage is there at the source side. So whenever the highest reverse voltage is there, their depletion region will be goes on increases. So that's why we can see here more depletion region. Here, this is a less depletion region. The internal one depletion region, it is due to VGS. That is fixed here. I'm not talking about this one. I'm talking about the outside one. Outside is more here, outside depletion region more here. Here it is less. And this is happening due to VDS. As this VDS is slowly increases, like 3 volts means again here it will become 3 volts, it will become 3 volts, it will become 2 volts like that. So again, if it is 3 volts means again this depletion region will be increased like this. So in this way, if I increase this VDS, this depletion region at the drain side also goes on increases. At one some particular point, it will reach to the maximum depletion region. It cannot increase more than that. Within the available channel, that electrons can move it. If you see this graph, like VDS and IDS, initially as increasing this VDS, current also goes on increases. At some particular point, it will go to the saturation region. This is called as a pinch of voltage actually. This is when VGS is equals to 0. If I give VGS in negative direction, let us say, if I give VGS in negative, then what happens? The channel will be decreases. The channel will be decreases, right? So if you see here, if I give VGS in negative direction, VGS in negative, then channel will be decreases. Channel will be decreases like this. More depletion region. In this case, more depletion region. So the effective channel will be decreases. Effective channel decreases means the maximum current also decreases. Then in that case, the same graph I'll get, but it is just below than this one, like this. This is when VGS equals to -1, -2, like that. In this way, we can see. The point, just take a snapshot of this one. What are the things we have been discussed? The same things are there in the points format. Now, this is the graph when VGS equals to 0. What is the case when VGS equals to -1, VGS equals to -2, like this. But because if I slowly increasing this VGS in a negative direction, means the effective channel will be goes on decreases. So that's why the maximum current also will be decreases, right? So these are the region of operations like ohmic region, saturation region, cutoff regions. This region, as we increase in this VDS, as we increase in this VDS, the current also increases. This is called as an ohmic region. As increases VDS, the current is constant. This is called as a saturation region. And cutoff region means this one, the lowest one. This is in a cutoff region. At some particular point of VGS, the channel is completely closed. And that particular point we'll call it, and from there onwards, we are indicating as a cutoff region. Now we'll see the construction of a P channel. Construction of how this P channel will looks like. Only one difference. Their channel is N-type. In the case of a N-channel JFET, channel is N-type. Whereas in the case of a P-channel JFET, the channel is P-type here. So if the channel is P-type, here the region should be opposite one, that is N-type. Very simple. Again, the rest of the things are same. Again, these two terminals are internally shorted. This is called as a gate, and this is called as source, and this is called as a drain. Very simple. The thing is that here channel should be P-type. If the channel is P-type, then the other regions which are connected with the gate terminal, that is N-type. That is the only difference. And then we can give a connections also here. How to keep the connection? The source is used to send the charge carriers. It has to send the charge carriers. It means here it was sending in a holes. It has to send in a holes means here we have to give a positive terminal, right? It has to give a positive terminal. It has to collect the holes. Collect the holes. Hole is a positively charged particle. So that is why here we have to give negative voltage. This we are calling it as a VDS. And at the gate side, it has to control it. Control the holes which are going from source to drain. It means that can be controlled with the help of depletion region, right? And that depletion region should be increased. And how that is possible? We have to give in a reverse direction. A reverse. We have to give a connection in reverse bias. How to give it? It is a n-type means here we'll give positive, here we'll give negative, and that we are connecting. This one we are connecting to source like this. This is an BGS. That's it. Very simple. This was a basic connection of a P channel JFET. Similarly, we can see the same graph. So these are the connections. These are the connections. Just go through it. And similarly, we can see the same graph. This was a transfer characteristics and this was a drain characteristics. And the rest of the things are similar. No need to discuss again. FET as a voltage variable resistor. Actually, this FET can act like a voltage variable resistor in the two ways. That is in the JFET, other one is MOSFET. I'm talking with respect to JFET. Actually, this topic is not new. Whenever we are applying this VDS, we already seen this, right? Whenever we are applying this VDS, in this case, as VDS goes on varies, maximum voltage will be drop across the drain side, minimum voltage will be drop across the source side. Due to this maximum voltage, depletion region at the drain side is high. The depletion region at the source side is low. In the resistance at the drain side, the resistance is initially low. As increasing this VDS, this resistance will goes on increases, but because depletion region is increasing. So the variable in that resistance with respect to the variable in that resistance with respect to this VDS is called as an voltage variable resistance. And that we can see it in ohmic region only. In the ohmic region only we can see that. Just go through it. Very simple. What are the things we have been discussed? The same thing is there over here. Just take a snapshot and go through it. Very, very important. If they given this one, then you must know that in general different diagram. Then you have to explain it out there. These are the points. Very important. Now, N-channel enhancement MOSFET. Now we'll see. In this case, to discuss this N-channel enhancement MOSFET, first of all, let me try to define its construction. Here also, I'm taking one pure semiconductor. One pure semiconductor. In this pure semiconductor, I'm doping within a trivalent impurities. Then it will turn into a P-type. I'm doping with trivalent impurities. It will turn into P-type. On the two sides of this P-type, it will be doped within a divalent impurities. That is, then pentavalent impurities. It will turn into an N-type. It will turn into an N-type. On the top of this one, silicon dioxide is formed. On top of this one, silicon dioxide is formed. That is insulating layer. This is silicon dioxide. This is an what is this? This is a substrate. This is a substrate. Actually, semiconductor, right? Now, here in this case, we'll try to connect the ohmic contacts with the one of the n-type. We'll try to connect the ohmic contacts one of the n-type. For that one, we are removing some part of the silicon dioxide and we are connecting with a metallic contact, metals, and we are planting with the metals. And this terminal we are calling it as a source. And this terminal we are calling it as a drain. And between these two, again metallic contacts is placed in between these two, and that we are calling it as a gate. That we are calling it as a gate. This is the construction. Actually, I already told you why it is called as a MOSFET in the sense the top one is a metal, this one is a metal. The middle one is an oxide, which is insulating layer. The downside is a semiconductor. It is a semiconductor. So metal, oxide, semiconductor fit. So that is the reason it is called as a metal oxide semiconductor fit. We can see the metal, in middle one is an oxide, and then semiconductor. So if you see the structure, it will looks like this.
So basically, he will take a P-type substrate. In that, we'll do, and one terminal we'll count it as a source, the other terminal we'll count it as a drain. In between these two, silicon dioxide is there, which is dielectric medium. We're implementing a gate terminal on top of the silicon dioxide. Now, source is used to send the charge carriers. We already know this. This drain is used to collect the charge carriers. Whereas this gate will control the charge carriers. The thing is that here, what are the charge carriers? It has to send the electrons. It has to send the electrons. It has to collect this electrons. But to send this electron, there should be channel should be there. In between these two, what are there? Holes are there. These holes will not allow these electrons to move from source to drain. That means there is no channel for this source. That means there is no channel from source to drain, right? So we have to create a channel and we have to control that channel with the help of a gate. This is all about enhancement MOSFET actually. In the case of a depletion MOSFET, this is an enhancement MOSFET. In the case of a depletion MOSFET, we can see only one difference. There is already a channel will be there. That is N-type channel is already there. That is a depletion MOSFET. This is the only difference between depletion MOSFET and enhancement MOSFET. In the case of enhancement MOSFET, no channel will be there. In the case of a depletion MOSFET, there is a channel will be there. Like this, there is a channel will be there. In the case of depletion MOSFET, right now we cannot see any channel. That is an enhancement MOSFET. Now we'll see the connections. This of this N-channel enhancement MOSFET. This is the point. Just go through it, take a snapshot, and go through it. Like we can see this, there is no physical channel will be there between source and drain. So that is the reason it is called as an enhancement MOSFET. Now we'll see this connection. Now we'll give a connection here. Now if you see here, this source has to send the charge carriers, which is source has to send the electrons. It has to send an electrons. It means it has to repel it. That should be connected with a negative. If I given a negative, then this electrons will repel from this terminal, and this electron should be collected at the drain side. It should be attracted, and that can be attracted with the help of a positive polarity. So that is why here I am giving positive to the drain, positive to the drain, and this we are calling it as a VDS. This voltage terminal we are calling it as a VDS. And at the source and at the gate side, if you see here, somehow we have to form a channel here, right? Here at the gate terminal, we have to form a channel. It means here we need an electrons. Here we need an electrons here. To form a channel means here we need an electrons. Here we need electrons. So we have to attract the electrons from the P-type substrate. Of course, in the P-type also the electrons will be there. They are minority charge carriers. We have to attract those minority charge carriers. So here we have to give to attract these electrons, we have to give gate within a positive terminal. We must connect within a gate within a positive terminal, and source is a negative terminal. Now let us see by changing this gate to source voltage what happens. If I slowly increasing this VGS, from 0, then what happens? Initially, it will try to attract these electrons. Actually, this will be works under the capacitance behavior. That we'll see in the next video, the MOSFET as a capacitor. The thing is that here, by giving this voltage, by giving this positive voltage, it will try to attract the electrons from the P-type substrate. So if I slowly increasing this gate voltage, it will try to attract more number of electrons in this channel. In that way, we can increase this channel path by increasing this VGS. Initially, there is no channel. So if you see this graph between VGS and ID, I'm keeping VDS as a constant. I'm slowly varying this VGS. Right. Now, if you see here, initially there is no channel will be there. Initially, and there is no channel. So that is why the current is also zero here. The current is also the zero. Initially, we cannot see any channel, so that is why current is also zero. As increasing this VGS, slowly channel will be formed. It means current will be slowly increases. At some point, the channel is completely formed, and if I slowly increase the VGS, the channel goes on decreases, the current also slowly increases like this. This is a graph, we can see it with VGS and ID, and it is called transfer characteristics. Actually, the amount of voltage to create a path, to create a channel, is in a threshold voltage. That is called threshold voltage. But because here to create the threshold voltage to attract the more number of electrons, here we need more voltage. Here we need more voltage. But because these are the minority charge carriers, it has to grab it. Initially, it will ripple the holes actually. There is a ripple holes. In the p-type, it will looks like this. Negative ion and then hole. It will ripple the holes. It will ripple the holes. Then hole will be removed from here. Then we left with only a negative ion. So after that, it will try to attract any electrons. These are the advanced topics. We'll see it in the MOSFET capacitance. But as of now, as VGS increases, then it will try to attract the electrons. As these electrons are minority charge carriers, it will have to apply the more amount of voltage, that is up to threshold voltage, then it can attract sufficient number of electrons, then the channel will be formed so that electrons can move from source to drain in this way. As increasing this VGS, again the channel width will be goes on increases, and then the current is also goes on increases. This is the one. Just take a screenshot of this one. Now VGS. And these are the points we have been discussed. Just take a screenshot. Now we'll see with the effect of VDS. Again we have to give the same connection. Again we have to give the same connection. This is VGS, but right now I'm keeping constant. VGS I'm keeping is a constant. VGS I'm keeping constant, and this VGS should be greater than this threshold voltage number. It should form a channel. It should form a channel. I'm assuming this. I'm assuming that the channel is already formed, right? Now I'm giving this connections here. It is negative. Here it is positive. Here it is negative, and it is positive. This one we are giving it as a VDS. Now, if you see here, as this VGS, I'm slowly increasing this VDS now. And again, the same thing. We have been discussing the FET, right? That is 3 volts. If I give it here, means the 3 volts will be maximum at here. It is somewhere around 2, 1, and here it is 0.5 volts, something like that. So again, we are giving this 3 volts for this N and P regions, that is the reverse bias. So that is why again here there is a formation of depletion region because of this 3 volts. If I give a 4 volts means again more depletion region will be formed. So in that way, if I slowly increase this VDS, initially if I say as increasing this VDS, the current also increases. But because the velocity of this charge carriers in this channel flowing, the flow of electrons in this channel, the velocity will be goes on increases. As increasing this VDS, the flow of electrons, the intensity of these electrons will also goes on increases. So that is why current also increases. Initially, current also increases like this. At some particular point, at some particular point, at some particular point, it will be maximum. It will be get saturated. After that, it will may even to increase in this VDS, the current will be almost like constant. It is almost like constant because of this depletion region. And this is also this concept is also called as a voltage variable resistance. And this region is called as a ohmic region. This region is called a saturation region. If I increase this VGS, then again I will get the same graph like this. Let us say this is the VGS at 4 volts, and this we can see VGS at 5 volts. But because VGS at the 5 volts, we can see the channel width is goes on increases. If channel width is goes on increases, if channel width is goes on increases means the maximum current also increases like this. If VGS equals to 3 volts means the same graph will be shifted towards the downside like this. This is the point at VGS equals to 3 volts. So this is an effect of VDS with respect to VGS. This is the graph, and this is called as a drain characteristic. These are the points. Just take a snapshot. Just take a snapshot of this one and take a snapshot of this one. All right. Now, the last topic is N-channel depletion MOSFET. I already told you, very small difference is there between N-channel depletion MOSFET and N-channel enhancement MOSFET. In the depletion MOSFET, we can see only the channel. We can see a channel here. This is the only difference. In the enhancement MOSFET, there is no channel. In the depletion MOSFET, there is a channel. It means here already we have a channel. Now you see, now analysis will become easier. Why? Because you already understood about this enhancement MOSFET. This is the basic symbol. This is the basic symbol. This was the structure of this depletion MOSFET. Now we'll see. These are the things these are the points about an depletion MOSFET. Like very simple. We'll take a p-type substrate. In that, N plus regions are placed on the two sides. In that, N plus regions are placed on the two sides, and N regions are placed in between this source and drain. On top of the silicon dioxide replaced, and with the help of metallic contacts, we have been indicated the source and then drain, and the metal is placed on the top of the silicon dioxide, and that we have to call it as a gate terminal. Like that. Even though the VGS equals to 0 volts, there is a presence of channel. There is a presence of channel. So that is why it is called depletion MOSFET. These are the points that are given here. Just go through it, take a screenshot and go through it. Now, directly coming to the connections now. So if you see here, in the case of a VGS, I can give two ways of connection. So if I want to attract more number of electrons over here, I have to give a positive VGS, positive terminal over here, and the negative terminal over here. Initially, I am wearing this VGS terminal. Initially, I'm wearing this VGS. What happens if I slowly increase this VGS? It will try to attract more number of electrons on this substrate. In that case, the channel also goes on increases. The channel also goes on increases. If you see this graph, if you see the graph of this VGS versus ID, as this VGS goes on increases in the positive direction, then it will try to attract more and more number of electrons. The channel width will be goes on increases. If channel width is goes on increases, the current also goes on increases. At the VGS equals to 0, the current is maximum. VGS, some current will be there. At VGS equals to 0, the current will be there. Let us say that current is IDSS. If I increase this VGS in positive direction, then channel width also increases. Then in that case, if I given some VDS, it is negative. If it is a positive, this VDS, then this as increase in this VGS, the channel also increases. Because of that, current also goes on increases like this. Goes on. Instead of that, if I give negative direction over here, if I give negative, hmm, it means here I'm giving negative, here I'm giving positive, here I'm giving negative, here I'm giving positive. I'm increasing this one again. It means it will try to repel the electrons. Instead of attracting, it will try to repel these electrons. These electrons will move away from this channel. It means the effective challenge goes on decreases here. If I increase this VGS in negative direction, because of this negative polarity, it will try to repel the electrons from the channel. In that way, the effective channel will be decreases. The effective channel will be decreases. And of course, the current will be decreases. This is the graph. So that is why we can see this is the graph there. We can see this one. This is the between VGS and ID like this. Now, in the here itself, we'll try to discuss about the VDS. We'll try to discuss about VDS. Now, we'll keep this VGS as a constant. We'll keep this VGS as a constant. Let us say this VGS is given with a positive terminal. This is negative and this is positive. So channel is there here already. Already channel is there here. If I'm slowly increasing this VDS, what happens? Again, the same thing. If I slowly increasing this VDS, the current also goes on increases. The current also goes on increases up to some point. This region is called as a ohmic region. After that point, again the current is will maintain a constant. It was like very similar to the N channel enhancement MOSFET. No need to discuss it again and again.
So let us say this is the VGS is equals to 3 volts, let us say. That is positive voltage 3 volts. If I give a VGS equals to 4 volts means the effective channel will be increases, right? In that case, the current will be again increases. Then the graph will looks like this. This is when VGS equals to 4 volts. If I decrease this VGS, then the effective channel will be decreased. Then the current will be decreased. So that is why this graph will be shifted towards downside like this. So that is why here at the VGS equals to 0, we'll get the graph like this one. If I slowly increase this VGS in the positive side, it will be shifted towards an upper side. If I give a negative means, then it will try to repel the electrons, right? So that is why this graph will be shifted towards the downside. This is the drain characteristics. This is the transfer characteristics. Just go through it. These are the points of effect of VGS. By increasing this VGS, what happens in the MOSFET? Just take this snapshot and go through it. And these are the points of effect of VDS. By increasing this VDS, by keeping constant of VGS, what happens? Just take a snapshot and go through it. Hope everyone understood the concept. If you understand the concept, then hit a like button and do subscribe. Thank you.